Ever found yourself needing to get smart on a tricky subject fast? Maybe for an important meeting, or just because your curiosity hit overdrive, but you didn't want to get lost in a sea of technical documents? Well, you've landed in the perfect spot.
Hmm.
Welcome to the Deep Dive, your ultimate shortcut to truly understanding complex topics. Today we're taking a deep dive into something that sounds, well, incredibly niche at first glance. Weld repairs. But trust me, this isn't just about hot metal and sparks. It's actually a fascinating look at the fundamental principles of safety, structural integrity, and yeah, high-stakes economic decisions often made under immense pressure. It reveals a surprising amount about how the world around us stays together, literally.
That's absolutely right. We're pulling back the curtain on the often overlooked complexities of weld repairs, drawing direct insights from a really authoritative source on the subject. We'll explore not just the how, the techniques and steps, but crucially, the why certain decisions are so critical. You'll hear about the surprising challenges that can crop up and the vital considerations that separate a sound
Our mission for this deep dive is pretty clear. Extract the most important nuggets of knowledge from our sources, giving you a clear, concise understanding of weld repairs, from that crucial initial assessment all the way through to the final stamp of approval. By the end, you'll have a whole new appreciation for that patch you might see on a bridge or a piece of heavy equipment. Okay, let's start at the beginning then. Why are weld repairs even necessary? Our sources identify two main scenarios where they pop up. First, during production, right? While something is actually being manufactured, think of a defect spotted on a freshly made pressure vessel. Second, in service. That means on existing structures or machinery that are already out there working.
right, doing their job.
And the reasons vary widely, don't they? From correcting manufacturing flaws to making quick, maybe temporary fixes on critical equipment that just can't afford long downtime.
Exactly. And here's a crucial distinction, one that often causes confusion. Weld repairs are fundamentally different from routine, scheduled maintenance, or, say, a planned refurbishment. Those are activities you can schedule, allowing ample time for proper execution. You plan for them.
Right, they're on the calendar.
Repairs, in contract, are almost always unplanned, unexpected. This unplanned nature is precisely what introduces intense time pressure, and with it, the dangerous temptation for shortcuts, which you really want to avoid.
Okay. Makes sense.
And this is why our source emphasizes that any fabricator must have an established policy, methods, and procedures in place specifically for repairs. It's all about being prepared for the unexpected.
Got it. So when you think about where these repairs happen, especially those local or on-site fixes, it often comes down to manually controlled welding processes, doesn't it?
Yes, often.
And the old reliable manual metal arc or MMA, that's a common choice, right?
It is. You could almost call it the Swiss Army knife of welding in the field. It's incredibly versatile, highly portable. You can take it anywhere. And you can find a huge range of consumables for it, which makes it adaptable to all sorts of different metal alloys.
Yeah.
Very handy.
But it's not all symbol fixes, is it?
Oh, definitely not.
Mm-hmm.
What's often underestimated, and what poses a significant challenge, is that a repair weld almost always introduces higher residual stresses
Mm-hmm.
and more distortion into the material than the original weld. Think about it like trying to perfectly mend a broken bone.
Right.
It might heal strong, but there are always new stresses in that area. It's never quite the same.
I see. So for certain common industrial steels, like carbon manganese and some low alloy steels, these are more susceptible to cracking when under stress from welding.
That's correct. They are. And for those materials, this means pre- and post-weld heat treatments aren't just a suggestion. They're often a definite requirement. It's needed to ensure the repair's long-term integrity.
Okay, so pre and post weld heat treatment. Critical. Now, here's where our source says it gets really interesting. Before a single spark flies or a grinder even touches the metal, fabricators face a complex decision. It's not just, can we fix it? But maybe more importantly, should we?
Exactly. That's the core question.
Our source outlines a series of crucial questions, almost like a decision-making matrix that must be answered first. Think of it this way. First off, is it even financially worthwhile to repair this item? Sometimes, replacement is simply the more sensible economic choice, right?
Absolutely. Cost benefit.
More importantly, can we genuinely guarantee that structural integrity will be achieved? Because if not, what's the point?
Precisely. Safety first.
Are there non-welding alternatives we should consider? We'll touch on that later. And critically, what caused the defect in the first place? Because if you don't understand the root cause, you're just fixing a symptom, aren't you? And the problem will likely just pop up again.
Exactly right. You're just chasing your tail otherwise.
Hmm.
Beyond those fundamental questions, they also need to decide how the defect will be removed, what method, and which specific welding process will be used for the actual repair. That's a technical choice.
Okay. And what about checking the work?
Right. What non-destructive testing NDT is needed to confirm the defect is completely gone before any new metal is laid down. That's crucial.
You have to be sure.
Definitely. Will the welding procedures themselves need reapproval? What about the impact of the distortion and those new residual stresses we just talked about? Does it require heat treatment? We mentioned that, but is it needed here? And finally, what NDT is needed after the repair to prove it's acceptable?
And who signs off on it?
Exactly. Who gives the final stamp of approval? The sheer number of variables is why repairs can range from, relatively straightforward to incredibly complex. It often requires various engineering disciplines to weigh in. It's truly a team effort, not just one person.
That's a lot to juggle. So what does this all look like on the ground? Can you walk us through a typical process, like a kind of surgery for metal?
Huh. That's a good way to put it. It really is meticulous.
Okay, so it starts with a detailed assessment, right? Using surface or subsurface NDT to understand the full extent of the problem.
Correct. You need to know what you're dealing with. Then the repair area is thoroughly cleaned. Super important. Contamination is bad news.
Then you identify and mark the excavation site precisely.
Yep. Know exactly where you need to remove material.
Next, the excavation procedure itself. That might involve grinding or maybe even thermal methods like arc air gouging.
It could, yes. And this is critical. And it often has specific preheat requirements depending on the material and the method.
Yeah, got it. Then, a crucial step. Another NDT check to confirm the defect is completely gone before any new welding happens.
Absolutely essential. You cannot weld over a defect. Only then do they move to the actual welding, following an approved repair procedure. And that procedure specifies everything. The exact process, the consumables, the technique, heat input, interpass temperatures, everything.
And only approved welders can do the work, I assume.
Without question. Qualified personnel only. Once the weld is finished, it's dressed cleaned up, given a final visual inspection.
Then more testing.
Yep. Followed by post-repair NDT. If required, there's post-repair heat treatment.
And then, you guessed it.
Final NDT after that heat treatment. You have to check it again after heating.
Right. Makes sense.
The very last step is applying any protective treatments, like paint or coatings. It's a comprehensive, step-by-step, sequential process. No skipping steps.
That really emphasizes the meticulous nature. And you mentioned earlier that this process looks different depending on where the repair happens, production versus in service.
That's right. That context changes things significantly. Let's delve into those two distinct scenarios. First, production repairs. These are identified during inspection while the component is still being manufactured. Still in the factory, basically.
Okay.
And it's important to understand that a discontinuity, like a small imperfection in a weld, only becomes a defect if it exceeds the specific limits allowed by the applicable code or standard.
So not every little blip is a problem.
Correct. There are acceptable limits. During the initial assessment for surface breaking discontinuities, things like small cracks or areas where the weld didn't fully fuse, methods like magnetic particle inspection, MPI, or dye penetrant inspection, DPI, are used.
Okay, and those tell you the length.
They tell you the length, exactly. For the depth, ultrasonic testing, or UT, is often employed. That looks beneath the surface.
Right. So what about getting the defect out, the excavation part in production?
Okay, for excavation in production, if a thermal method like arc air gouging is used, it might even require its own procedure qualification.
Why is that?
Because the intense heat can affect the metal structure, the metallurgy right next to the gouge. And that could potentially cause new cracking if you're not careful.
Okay. So preheat might be needed there too.
Often, yes. Preheat is frequently necessary to prevent this cracking during gouging. Our source advises that the depth-to-width ratio of the excavated groove should ideally be around 1 to 1.5, though 1 to 1 is generally the minimum acceptable. And a vital cleaning step after gouging is grinding the repair area back by maybe 3 to 4 millimeters to bright, clean metal.
Why specifically?
To remove any potential contamination, like carbon pickup from the arc gouging process itself. You need pristine metal for the new weld.
Makes sense. And then NDT again.
Absolutely.
Hmm.
After excavation, NDT must confirm the defect is totally gone before rewelding, no question. And after the rewelding and any necessary post-weld heat treatment, or PWT, or NDT is performed to ensure no new defects have been introduced by the repair process.
Okay, so that covers production. What about in-service repairs? You said these are often much more complex.
They really are. This is where things get truly fascinating and honestly much more challenging. Here, the component is already out in the world doing its job. It's often in a different physical position or condition than it was during manufacturing. Think about the practical challenges.
Like what?
Well, the component might have been in contact with toxic or combustible fluids. That immediately brings in major safety protocols, permits to work. It's a whole other layer.
Right, safety hazards.
The welding procedure itself might need to be drastically different from the original one used in the factory because of the field conditions, access, position, environment.
Okay.
You have to consider the heat's effect on surrounding things, maybe sensitive electrical components or other materials nearby that don't like heat.
Things you wouldn't worry about in a workshop.
Exactly.
Hmm.
Performing crucial pre- or post-weld heat treatments can be incredibly difficult out in the field, sometimes almost impossible. And simply getting access to the repair area is often a major hurdle. Think working high up or in a confined space.
Yeah, I can see that.
And for large fabrications, bridges, big tanks, ships, these repairs often occur on-site without shutting down the entire operation.
Wow, so working around ongoing operations.
Yes, which adds yet another layer of complexity and risk management to an already challenging task.
So what's the absolute most critical thing for these in-service repairs?
Hands down, determining the exact reason for the failure and the precise material type, especially its chemical composition. You have to know what you're dealing with. Our source strongly underscores this. If you fail to conduct this cause-effect analysis rigorously, the repair itself could be unsafe, potentially disastrously so.
So understanding why it failed is the absolute bedrock.
It is. It's the foundation for making a sound, safe, and importantly, a lasting repair. You don't want it failing again for the same reason.
Given all this complexity, especially with in-service repairs, I have to ask, is welding always the best method? Or are there times when counterintuitively maybe it's the wrong approach?
That's an excellent question. And the answer, perhaps surprisingly, is no. Welding isn't always the best solution. Sometimes it's not even a good solution.
Really? Like when?
Well, sometimes, for a local irregularity or maybe a shallow defect, simply grinding out that defect and then blending it smoothly into the surrounding surface can be an acceptable, even preferable alternative.
Just grind it out.
Yeah, if it's minor enough and the code allows. This is particularly true if the steel happens to have poor weldability, meaning it doesn't respond well to welding heat, or if the component is under severe fatigue loading,
Fatigue loading meaning?
constant back and forth stress, cyclic loading. Our sources tell us it can sometimes be better to slightly reduce the cross-section, and thus the theoretical safety factor this way, than to risk introducing new defects, stress concentrations, and those high residual stresses into a brittle material.
Brittle materials being things
Like some thick-section steels or maybe cast irons. These materials might simply not withstand the stresses from heavy weld repairs, especially if any tiny micro defects are left behind.
So it's a judgment call.
It's all about making the smart, safe choice for the specific material and the specific situation. Sometimes less is more, in a way.
So if we connect this to the bigger picture then, even if a repair seems routine because you've done similar ones before, the devil is really in the details, isn't it? You can't assume.
Yeah, absolutely. You hit the nail on the head. It is vital to check for subtle differences, even if it looks the same. Perhaps the section thickness is actually greater this time, or the steel might be from a different batch and slightly less weldable, or the level of restraint, how rigidly the part is held, is higher.
And those small differences can matter a lot.
They can matter hugely. This is precisely where detailed due diligence truly pays off. It prevents a seemingly minor oversight from escalating into a potentially catastrophic problem down the line. Never assume.
Okay. Now let's dive into a few more specific technical considerations that demand attention before repair. Our source highlights some areas where you can get those real aha moments, showing just how many variables are at play.
Right. Let's get into some of the nitty-gritty.
First up, base metal composition and weldability. If the original drawings aren't detailed enough, or maybe you suspect problematic materials are involved, like certain free machining steels, you mentioned those can cause hot cracking during welding.
That's right. They contain elements like sulfur that make them easy to machine but terrible to weld. If there's any doubt, a chemical analysis is, well, it's non-negotiable. You're looking for specific elements. Nickel, chromium, molybdenum, copper, vanadium, niobium, boron, as well as the basics like carbon, sulfur, phosphorus, silicon, manganese. They all affect weldability.
And that analysis, even if it costs a bit up front.
It's a critical step. That small cost can literally prevent a valuable component from being ruined during the repair attempt. Or it might save money by showing that extensive, costly preheat isn't actually necessary for that specific piece. Knowledge is power here.
Got it. What about the required strength of the repair? You'd think stronger is always better, right?
It seems logical, but it's more nuanced than that. The higher the yield strength you demand from the repair weld metal itself, the greater the residual stress it introduces into the whole area. We keep coming back to that.
Right, stress.
That means a higher risk of cracking, and you'll also see more distortion of the part. Plus, it makes developing the actual welding procedure much more difficult and sensitive. For most conventional steel weld metals, there's a practical limit to this strength, maybe around 1,000 newtons per square millimeter, give or take. Pushing beyond that creates exponentially greater problems.
Okay, so aiming too high on strength can backfire. What about preheat tolerance? You mentioned preheat is often needed.
Yes, but while it's often necessary, especially for thicker or higher carbon steels, a high level of preheat makes conditions incredibly tough for the welder. Imagine working inches away from metal heated to hundreds of degrees.
Yeah, it must be brutal.
It is. And it can also surprisingly damage the parent steel itself if that steel happened to have been tempered at a low temperature during its initial manufacturing. The preheat could ruin its properties.
So are there alternatives if high preheat is problematic?
Sometimes, yes. You might look at using special ultra-low hydrogen consumables, which reduce the risk of hydrogen cracking, or even switching to non-ferritic weld metals.
Like stainless steel.
Exactly. Like austenitic stainless steels or nickel alloys. They behave differently during welding and cooling, and can sometimes avoid the need for such high preheat, though they bring their own challenges.
Okay. And what about the area right next to the weld, the heat-affected zone?
HAZ.
Right, the HAZ, the parent metal that gets heated but doesn't melt. This zone can either soften or harden, depending on the original steel and the welding heat input. Softening is likely in very high-strength steels, which can obviously reduce their overall performance in that area.
And hardening.
On the flip side, excessively hard HAZs are particularly vulnerable to something called stress corrosion cracking, especially in specific aggressive environments, like those containing hydrogen sulfide, H2S, wet sour service, and oil and gas, for example.
So you need to control that hardness. Absolutely. To counter this risk, a specific maximum hardness limit is often critical. Maybe below 248 HV is a common figure. This might require post-weld heat treatment specifically to soften the HAV, provided you've managed to avoid cracking during welding in the first place.
Which brings us neatly to post-weld heat treatment, PWHT itself, its practicability and necessity. You've mentioned it a few times.
Yes, because it's often desirable, maybe even required by code, for improving toughness or corrosion resistance or relieving stress, but PWHT isn't always possible or practical.
Especially for those in-service components.
Exactly. Trying to heat treat a massive structure already installed in the field. Very difficult, sometimes impossible. Even local PWHT, where you just heat the repair area, needs to be done very carefully.
Why is that?
If it's not done precisely, with the right temperature gradients and controls, it can actually introduce new problems and undesirable residual stresses elsewhere in the structure.
Wow, okay. Lots to consider. What about things under constant stress or vibration? Fatigue resistance.
Crucial point. If a repair is in a highly stressed area, or one prone to fatigue cracking, you can generally expect the repair to have inferior fatigue life compared to the original unwelded material. Unless the weld surface is meticulously ground perfectly smooth and is completely free of even tiny defects or sharp transitions, any notch is a stress raiser.
And what about certain types of welds?
Well, our source makes it clear. Fillet welds, where you can't access and grind the root smooth, they are simply not acceptable in high fatigue areas. The root acts as a built-in notch.
Got it. Okay, nearly there. Environmental resistance. This sounds broad.
It is. Beyond just general rusting or corrosion, you have to think about more insidious things. Stress corrosion cracking, which we mentioned cracks forming under stress in a specific corrosive environment. Or corrosion fatigue, where constant stress cycles and corrosion team up to cause failure much faster. There's also thermal fatigue from repeated temperature cycles and high-temperature oxidation.
So the filler metal choice is key here, too.
Absolutely. The filler metal chosen for the repair needs to be at least as corrosion resistant or noble as the original parent metal, sometimes even more resistant. And again, for issues like stress corrosion, PWHT might be necessary not just for stress relief, but to restore the correct microstructure in the HAZ and reduce its hardness.
All of which feeds into the last point here, inspectability and testability. How easy is it to check the repair?
Exactly. For critical service, you often want the highest level of assurance, so techniques like radiography, X-ray, or ultrasonic examination are preferred for finding internal defects.
Yeah.
However, some materials, like those austenitic stainless steel or nickel alloy fillers we mentioned as alternatives,
Yes.
they can present challenges because they often cannot be reliably assessed by magnetic particle inspection, MPI. Their material properties interfere with the method.
So the inspection method has to match the material too.
Precisely. And this all reinforces why critically conducted procedural qualification tests are so important before the real repair. You need to prove the procedure can make a sound weld that can be inspected effectively, avoiding hidden cracking or serious defects introduced by the welder or the process itself.
That's a huge amount of technical detail to manage.
It really is. And all of these intricate technical considerations, which seem purely mechanical or metallurgical, ultimately boil down to one crucial final insight for any repair weld, highlighted in our source. It is vital to ensure that the welders doing the work are properly motivated, understand the criticality, and are carefully supervised.
The human element.
Absolutely. It's so critical to the success of these complex, often high-stakes repairs. You need skill, focus, and diligence.
We've really covered a lot of ground in this deep dive, haven't we? We've gone from the fundamental reasons why weld repairs are necessary, looked at the complex decision-making process that guides them, walked through that meticulous step-by-step procedure, highlighted the critical differences between production and in-service repairs, and then delved deep into the intricate technical factors, material science, stress, heat treatment, environment that determine whether a repair truly succeeds or potentially tragically fails.
Indeed. I think what our source material truly underlines is that weld repair is far, far from simple. It's not just patching things up. It's a precise engineering discipline that demands a deep understanding of metallurgy, careful planning, meticulous execution, and constant vigilance. And the gravity of getting it wrong, the potential for catastrophic consequences, financial and human, is something that simply cannot be overstated. It's serious business.
Absolutely. So, with all we've discussed today, here's a thought to leave you with. Consider the next time you see a piece of heavy machinery, maybe a construction crane or a structural beam in a building or even part of a bridge, and you notice a visible patch or a repair weld. What new questions does that site raise for you now? Questions about the choices made, the risks that were considered, the environment it's in, and the sheer expertise required to ensure its ongoing safety and integrity. It gives you a whole new way to look at the engineered world around us. Thank you for joining us on this deep dive. We hope you'll keep digging into topics that intrigue you. Until next time.